So, yeah, thank you, Slavi. My name's Frank Kelly. It's a pleasure to come here and speak at PyData in this glamorous location. I'm going to talk about hierarchical clustering. Can everybody hear me okay? Yep? A bit louder. So, yeah, can I have a show of hands? Who here uses clustering on a regular basis? Let's say. Probably about half. So, and who has used hierarchical clustering? Okay, about a third, I'd say. Yeah. Okay, good to know. So, my talk is going to. I didn't know how to approach it, but I decided to start with a bit of theory, looking at, say, the origins of clustering itself. Go into hierarchical clustering as a method. Look at some performance metrics, things you can use, and then go across to Python, looking at Scikit Learn, and just talk a bit about my own use case I'm currently working on. And at the end, I was going to focus on some visualization options. So, who am I? So I'm actually, I say I'm a data scientist, but I studied engineering, so masquerading as a data scientist, but I did study electrical and information sciences, so it's as close as you can be to computer science and yet still be an engineer, you could say. I've worked for 10 years as an engineer, so I've worked in several different countries, including Norway. That's a reference to Norwegian. And I'm not I haven't been a heavy Python user up until quite recently. In my most recent roles, I've been more of a MATLAB sort of person. That's the way we engineers, that's the way we're brought up. So along with a bit of C++. So I'm making the transition. I've been forced in my new company just to use Python. So I'm getting there slowly. And obviously coming along to these PyData events helps no end. So I did set up a startup a couple of years ago, which does on-page optimization via machine learning. But now I'm working as a pure data scientist rather than sort of general CTO, data scientist and entrepreneur. I'm focusing on the data science part. So that's my transition. It may seem a bit of a crazy journey, but this is where I am at the moment. So I thought I'd start with just a recap on clustering for data scientists. And so obviously a collection of objects deemed to be similar, and this is a problem with inputs and no outputs generally. You're using some notion of similarity, so you can't actually define what a cluster is because it depends on the way you're determining the similarity between objects. And whilst you have no outputs to compare, if you're using some performance metrics, you may be comparing your groupings with some kind of structure, or so you could, if you're iteratively improving your clustering algorithm, you could say that you have outputs on the problem. So where did clustering come from? So it came really from anthropology, so the study of humans. And it's still being used today in this field. So you can see here plotted sort of race segmented by DNA. DNA is obviously a very high-dimensional problem, but here it's been nicely transformed into 2 dimensions. So we can quite easily see clusters, their proximity to each other, highlighted different colors and nice little shapes there. It's also at the same sort of period, 1930s, it was also used by psychologists to group people according to certain attributes, generating these psychological profiles. You may have heard of Carl Jung, for example. There are diverse applications. There's a few here. So outlier detection is one. Recommender systems. So you're just helping users deal with an overload of information. An outlier is obviously something that's far away from a cluster or other clusters. It's used in image processing for the purposes of, say, compression, for example. And you can actually cluster time series. But none of these are the application I'm going to talk about, which is text clustering. Two main purposes behind clustering, which I think we're all aware of. So one is exploratory analysis, so from a data mining perspective, understanding the data set. And you can use it as a standalone tool to just do that. Also, it may be a component of sort of a supervised learning process. So you may want to cluster your data before you apply models to it. So, what are considerations when we are getting ready to do clustering? First of all, we want to think about the way we're partitioning. Do we want a single level, like a flat structure? Or are we more interested in multi-level clusters, like a hierarchy? Because I've seen, attending Kaggle competitions, I've seen that people often just jump into k-means or something without even really thinking about the data set that they're looking at, for example. We need to consider separation. Can objects belong to multiple groups, or can an object only be within one group? And the way we actually define similarity, do we use some kind of distance, like Euclidean distance as the crow flies, or are we looking at something like density, continuity? And also, finally, we want to think about the dimensions. So the example I showed earlier was a clear example. With DNA, you'd struggle when you've got a crazy number of dimensions. So you need to think about that. So my use case is search keywords, search keyword terms. The company I'm working for is called Analytics SEO. And they hold a lot of data regarding keywords, and they basically query Google and other search engines on a large scale and build up a picture for the clients of which keywords you're ranking for. So say this is a client. I have pages belonging to that domain, and they have a certain number of keywords that they rank for. So you can then go from the other side. You can look at other pages that rank for the same keywords. You find out who is your competition. Sometimes there are sort of surprises because your online competition may not be, if you're a retailer, say, may not be the same as your typical high street competition. So, for example, Snow and Rock, they sell snowboards. They assumed that they would be competing with ski shops and ski suppliers, but they were mainly competing with, say, Debenhams or mainstream retailers. So you're gathering a lot of keywords, and the ratio of, say, on the left you have your common keywords, the keywords that you rank for and your competitors rank for, and the opportunity keywords on the right. So so these are keywords that you don't rank for currently, but if you started to incorporate them into your website, you might rank for these, and therefore it's an opportunity. But there are far more on that side. So with this process, say this is, for example, for a law firm, you come up with all these fantastic keywords, but you have 100,000 of them, and you can't just pass them on to a client. So you've got a lot of data to play with there. How do you go about presenting these to a client? The client's got a few questions. The client's got their own structure on their website, so they've determined how to structure their website. So they made assumptions about what people are searching for, and they often want to know: does my website structure match what my client base is searching for online in my sort of domain? And then secondly, where is the money? I've got 100,000 keywords to optimize. What is the quickest route to cache? And you can start to weigh up which keywords have the most search volume, which you have no hope of competing for. It might be Amazon have got covering a lot of your keywords. It might be very difficult to move in certain areas, but there may be key areas where you can absorb these keywords and make them a part of your website. And finally, there's relevancy of keywords. You might be ranking for words that just really have nothing to do with your business. So this is just underlying the sort of website-like structure that clients want to see. They want to get visual insights, and people deal very well with structure. People like orderliness, they like hierarchy. So this is basically the remit. There's also the idea of allowing users to feed back in, to start to adjust clusters and groups and give their own input. So how do we cluster text? Now Slavi, who introduced me, he actually did a really good talk about a month ago on LDA, which was really interesting. So that's like a topic modeling approach, a bag of words approach. But the thing with that approach, it doesn't give you this hierarchy that I was looking for. You can actually use good old k-means clustering if you're using the correct distance measure, because really the values that you're clustering are to do with word frequencies. And of course, when you're clustering text, it's very high dimensional, very sparse vectors. So, decided upon hierarchical clustering, I want to bring structure to our client's data. So, two main types, agglomerative and divisive. So, and if you think about the deterministic, it's not like k-means where you might randomly assign your starting points and then you iterate. Here, every time you do it, you get the same result. Agglomerative, you start with sort of many singleton clusters, and you just go through them. You're merging two at a time, and you build up your hierarchy. And again, divisive is basically the opposite. So you're just splitting. You're going the opposite direction. You're splitting large cluster into much smaller. So how do you determine when to merge? You need some kind of like a sort of agglomeration factor or method, okay? So there's a concept of a linkage type. So you can choose, so you're just comparing the similarity of items, right? So you might compare the two most similar items in two clusters before you make your decision to join them. Or you might compare the two most dissimilar elements. And hang on a sec. So, the problem with both of these approaches, they're quite sensitive to outliers, as I'll demonstrate. So, if we were clustering countries in the Americas, using and within those clusters there were cities, you might join by the single approach. You might bring together Havana and Miami, but with the sort of the other approach, you might bring together a remote outpost in Alaska with Santiago de Cuba, if you're going to join those two countries, and you can see the problems it might cause, because there you've sort of absorbed part of Canada as well, and it's kind of it may not be the best approach. So there are other ways. So average link looks at similarity between all pairs of items in the two clusters. But as you imagine, if it's the number of items in the first cluster times the number of the second, so computation is very expensive. There's a way around this though, and that's to take the centroid. So you're just looking at the similarity between the center of those two clusters. And then here's a method it's quite prevalent, and it's to do with minimizing the variation within a cluster, basically. But Ward, when he defined it, he said you could basically minimize any function that reflects your purpose. And I think it's a good way to look at it. Keep your options open. But what you're doing is you're minimizing the sum of squared error, and you're reducing your variation before you make any decision whether to join clusters together or to divide. So I'm just going to talk briefly on divisive clustering. It's a top-down approach, and when you split, you use the Ward's criterion. You can say, yeah, it's a more of a global view, and apparently it's more efficient. It's not, as far as I know, implemented in Python or Scikit Learn, so I haven't looked at it. One challenge you have to have is to avoid getting really tiny clusters. You obviously have to have a stop point before you basically decluster everything. So again, looking at your data set, you need to match a similarity measure to your task in hand. So if your data is purely numerical, you might want to start using Manhattan distance. So this is basically distance, bit of Pythagoras there in 2 dimensions, distance the crow flies. If your data is binary, you can apply sort of Jacquard coefficient. But for text, you should really use something like cosine similarity, because the way you represent your data is going to be usually in a vector full of frequency of particular terms, which could be word, which could be a topic, which could be a phrase, for example. So you can basically take the 2 vectors and perform this cosine similarity. It's quite straightforward. So within Python, we're very lucky to have Scikit Learn and its agglomerative clustering module. It's the same, there's also k-means clustering available. I'm going to go through the process I went through with agglomerative clustering. So one sort of piece of advice is try and, if possible, if you do have extra features available, I would add them into your data set. So I knew which pages each keyword was ranking for. So I actually went to the URL of each page and took words from the URL and aggregated these to the keyword set. So it adds to the variation of the data set, and yet brings in sort of some inherent structure from the website. So I just running a function here which joins the words from the URL to the keyword. Once you've done that, so basically extracting the keywords there. Some advice on prepping your text. Like I said, add some features. Also, stemming words can be a great idea, because some words are very similar, but they might have an apostrophe or different ending. But I would be a little bit careful choosing your stemmer, because there are some that are quite severe. Within NLTK, there's one called snowball stemmer, which actually takes plurals into account and things like that. So it's a little bit less harsh. It still gives you what you want. Low frequency cutoff, so you're not really interested in words that just hardly appear, basically. So you might want to experiment with this value. You can set it. And same for words that just appear everywhere. So they're not really helping you in your objective of clustering. So another useful feature is n-grams. So you're not only clustering individual words, you can look at bigrams and trigrams, whatever you want, really. As long as you're keeping the ordering of the words, then it makes sense to basically add features to your set. So, foreign languages it's difficult with keywords because you can, like, for example, we operate in the French market. You might have English language keywords being searched for in France. But ideally, you want to separate it completely, so you do a completely separate analysis in French. It's a bit of a challenge, really. So here, preparing the text, I'm using a vectorizer, just doing all the things I said earlier, getting rid of some accents, determining like a token pattern where I had to spot a word. And I'm deciding to use 1 and 2 word n-grams. What I'm doing at the bottom there is I'm actually transforming this data. I'm just taking it to a sparse matrix, basically. So it's mainly zeros, and I'm just plotting what the data looks like at the bottom. So, yeah, dimensionality is a whole topic. You could have a whole presentation on that, but there are pros and cons with text analysis. I think if you want to visualize your result quickly, I would try and reduce the number of dimensions, and spectral clustering is one way to do it. So what I'm doing here is I'm actually at the top, I'm taking the sparse matrix and transforming it into 2 dimensions. And I'm trying the linkages I spoke about earlier, so the Ward, average and complete. And I'm also trying different distance measurements, Euclidean and cosine. But there are limitations here. So, for example, in Scikit Learn, you can't. So let's get this right. So yeah, for Ward linkage, you can only have Euclidean distance, which when you're clustering text isn't ideal, for example. So I think this is a relatively recent library, but I think they need to add universality of distance metrics. This is what it looks like when you plot the data put into 2 dimensions. So I've just selected 8 clusters, for example, out of I think 3,000 keywords, and you can see some groups emerging. This is with the Ward linkage, and it's quite effective, although you can probably observe there's not enough groupings there. I chose 8 because it matched the average number of pages per site in this set of domains I was looking at. So you'd have to, experiment, try different numbers of groupings. Here's using cosine distance, but because Ward linkage didn't support it, I had to use average linkage. You can see it's like it's a very different approach, and it's actually here's nicely clumped, but here everything is spreading out from a central point, and the result may not be particularly nice to look at. So another thing you can do is plot a dendrogram, and this is what one looks like, broken down into 5 clusters. But dendrograms, I don't know what you guys think as data scientists. I personally wouldn't present one to a client. I struggle to present it to my team, to be honest. And it sort of gives a seal of approval. They can see that you're a data scientist, you're doing technical things, but I wouldn't, outside of the company, you're going to have problems presenting one of these things, I think. So to assess the quality of your clusters, you can apply various metrics. So you could examine the clusters internally and just see how pure they are, homogeneous. You can also apply external metrics, so you can compare groups of clusters and you get measurements such as the adjusted rand index, normalized information index. Which brings me on to topic modeling, which is quite a task. Usually, when you run an algorithm, you're able to extract the most common, for each cluster you can extract the most common terms per cluster. But then you can end up with like a huge long string of meaningless words. So one way to deal with this is to do the sort of 90-10 rule or 80-20 rule, and take whichever words have 90%, whichever words fill up 90% of probability. But you might want to have a cutoff, because you could still have about 10 words, and you've got to produce something that's meaningful. Another problem is when you start to stem words, you get all the stem words appearing in the topic names. So you have to build what I did was to build an unstemming module to make the words complete again. But this has varying, impact as well. So hierarchical clustering beyond Python. I've got a few minutes left. So here's something I decided to do. I figured with Python I was loading a lot of data from a database, doing some analysis, playing around with it, and then storing it back again. We started to use this NoSQL database called Elasticsearch. I guess some of you may be familiar with it. It's a document store, but it has analyzers built in, and it can do things like term frequency, inverse document frequency, and stop words, and it has language-specific analyzers within the, as you store the data, you can just run these things on it. So I really recommend having a look at Elasticsearch. Very easy to get going. You basically store a document like this. So I'm able to store a page keyword, for example, cheap holidays in South Africa, and I can run an algorithm which does hierarchical clustering off the shelf. I can run that algorithm directly on the database. So it's doing all my stemming, it's doing all my text processing, it's dealing with multiple language support. It really does everything you need. So you don't have to spend all this time going through the individual steps and then finding out the limitations of individual models, for example. So I'm going to try and demonstrate that. So, oops. Yeah. So this is, so if I just run this now, this is just me running clustering on a set of documents in Elasticsearch. So I just press return, and boom, it's just clustered all my documents for me. And it's come up with, it's done all the topic labeling for me. This is just a flat structuring. But there is a hierarchical option available as well. But I just thought it was a very nice solution. And Elasticsearch, it's really powerful for text search. Obviously, it's sort of all optimized for this sort of thing. They currently have 3 clustering algorithms. The first 2 are included for free, but the third one you have to pay for. But the third one is like full hierarchical clustering. So I recommend you look into it. I can sort of demonstrate it here. So if I do a Google search, a search on their, they've got this demo page where you can just run a search for some words, and they have this visualization, which this is just set to frequency of word occurrence, and it's a very nice way of just visualizing your set of keywords, for example. Okay. So something else I did was to run it on our keyword set. So I just wrote a script in Python to convert to the format that this visualizer reads. This is sort of like a JavaScript object. And I it's a bit too zoomed in here, but I weighted each cluster by the sort of opportunity in terms of return on investment for the client. so they can see very quickly, you know, which words to focus on. It doesn't show up very well here, but if anyone's interested, I can demo it after. So yeah, maybe tie up this sort of visualization with Elasticsearch. You can access Elasticsearch quite easily from Python, and yeah, and that's basically it. So thank you very much. Anyone have any questions? Yep, at the back. Just very short terms. Usually.
Can you repeat the question?
Oh, sorry. Yeah. So have I been using it on large text documents or very small ones? Effectively, is what you're saying?
Yeah, pretty much. Just to do with whether or not there's like with Elasticsearch, you just can have bulks of text to deal with things like more like this kind of queries. And the issue that I found when using Elasticsearch, particularly when trying to do something, you know, along the lines of clustering, is quite often the document length can have like an impact. So as a result, we actually have like lists of words that we want to basically cluster within Elasticsearch, and each list of words represents like a user's interests.
Yeah, I see no problem with taking that approach with Elasticsearch. Yeah.
Yeah, it's very interesting because this is the first time I've heard of clustering in Elasticsearch, so it's very insightful.
You should look up Carrot 2. That's the algorithm. I've put the links in the presentation,
Yeah,
which I think will distribute.
All right, thank you.
That's all right. Hi there. Yeah.
Yeah, really interesting talk. Thanks. I want to hear your opinion on combining. I wanted to hear your opinion on combining different types of features in a document feature vector. So say, for example, you have TF-IDF features, but then you have other features as well, which might be on a different scale. So maybe categorical features that might be binary. Do you think it's okay to combine those types of features into one long vector, or what's your view on that?
It's a good question. It's not something I've done before. Maybe there's somebody here who's better qualified who can answer that. So combining categorical with sort of text vector. This guy here might have an answer.
The meaning gets lost if you combine categorical and numerical features. So it's kind of, you have to either keep it pure binary or keep it pure numerical. But
Okay, so keep it pure is the message. Yeah. Any other questions? Yep.
So how do you come up with
Yep. So how do you, yes, just asking how do you come up with a cutoff for agglomerative clustering or divisive, I guess. Well, it depends on your use case. For us, the clients wanted to see initially some structure that matched their own website. So I just took a straw poll of all the websites in their market and just looked at the number of pages per site. I think you just experiment. That's what I can say. Any other questions? Sure.
Have you thought much about combined
I haven't thought about it. I'm quite new to this field myself. So far, we've just been summarizing data and doing it on a batch process, as you say.
And with Carrot, what's your experience with performance once you go to large document sets? Does it perform fairly well?
So, yeah, performance of Carrot 2. So, actually, going back to your previous point, I think in terms of online, Carrot 2 is great because it just acts on whatever data is available in the database. So in a way, if you're continuously updating the database, it is a form of online in a sense. In terms of performance, yeah, there is. It does start to slow down. The demonstration I just did, I think, was 1,000 documents. It just took a sample of my overall set. But the thing is, for us, it's just a one-time action, and it happens in the background. It's not part of the front end, so it wasn't a key feature. But yeah, they offer different options. They offer, I think, for this Lingo 3G algorithm, they offer different pricing categories, and you should talk to them directly to find out ways to improve your performance.